Hello and welcome to the first video from Toro 3D. My name is Mike and today I'm going to tell you my thoughts on the ideal Gantry material for high temp CoreXY 3D printers. In this video I'm going to give you a deeper insight into materials and mechanical engineering. It's not going to be a presentation about a specific product. Before we get started, here is a quick reminder of how the CoreXY principle works. You have two stationary motors and two belts, shown here in red and blue. What is important for this video? For a movement in Y direction, a force acts on the idlers as indicated by the orange arrows. So the force to the printhead is applied through the gantry. With that in mind, what properties does the ideal gantry have? Ideally, it should have zero mass, both for high physically possible accelerations and good input shaping results. Also, it should have infinite rigidity to not rotate or bend when it's accelerated. Let's start by talking about the material of the support structure, because this will impose some restrictions on the geometry. In practice, zero mass and infinite rigidity translate to a high Young's modulus to density ratio. As you would expect, there are already resources available that can give us this information. Let's look at one together. This graph shows the density plotted on the x-axis and the Young's modulus plotted on the y-axis. Please note the logarithmic scale. Each of the parallel angled lines represent the same Young's modulus to density ratios. So for instance, commercially pure lead has the same ratio as some rigid polymer foams. We are looking for a high ratio and therefore are interested in the lines at the very top. I'm going to disregard the technical ceramics, shown in yellow, since aside from their brittle nature, even the cheap ones like aluminum oxide, alumina in the graph, are too expensive. The next best thing are composites, shown in dark red, which do cover a wide area as composite by definition simply means made of several components. However, I'm going to make an educated guess that the top ones are high modulus carbon fiber composites with a 65 to 70% fiber volume fraction. Now if you're grinning because you're currently using a 40 euro gantry you got from China, then don't get too excited. It does not have high modulus fibers in it, and I'm willing to bet the fiber content is not at the high end of the spectrum. And of course there's the matter of fiber orientation, which needs to match your load case. If we go down a little further, we end up at the common metals. And I would reckon that common carbon fiber tubes can also be found here. We have steel in the top right corner with a density of 7.8 kilograms per cubic meter and a Young's modulus of 210 gigapascal. Titanium with a density of 4.5 kilogram per cubic meter and a Young's modulus of 105 gigapascal. And aluminum with a Young's modulus of 70 gigapascal and a density of 2.7 kilogram per cubic meter. In terms of the Young's modulus to density ratio, aluminum and steel are essentially on par and titanium is a little behind. Another important factor is the thermal expansion. Before I explain the bimetal effect to you, let's look at some material data. This table shows the thermal expansion coefficient, which has the unit per Kelvin. It tells you how much a material expands when you heat it up. Bearing steel has a thermal expansion coefficient of 10 to 12. Continuous carbon fiber composites in fiber direction of roughly 0. This is because the fibers have a negative thermal expansion coefficient, which cancels out with the positive thermal expansion coefficient of the epoxy matrix. Aluminum has a thermal expansion coefficient of 23 and titanium 8.6. Now with that in mind, let's take a look at the bimetal effect. Here we can see a schematic of a typical gantry with a steel rail on top of an aluminum structure. When you assemble it, everything is nice and flat. So what happens when we heat it up? Both materials will expand, but the aluminum structure will expand roughly twice as much. Since both materials are joined at the interface, the whole assembly starts bowing. In terms of the magnitude of the bimetal effect, it makes no difference if you use an aluminum or carbon fiber gantry. It will just bow in different directions. Since it takes a while for everything to heat up, the bowing will continue even after the air in your chamber has reached its final temperature. This will result in a time-dependent bed mesh, which is a big annoyance. Because when the deformation continues after you determine your bed mesh, your first layer will not be perfect. Currently, people heat soak their printers for long periods of time to address this problem. The better alternative, however, is to choose a material for the support structure that has the same thermal expansion as steel. The last aspect that has to be taken into account is manufacturability. The support structure needs to be tube-shaped in order to have a high torsional rigidity. Why? Because open profiles have a very low torsional rigidity, and you can easily test this at home. Try twisting a paper towel roll along its longitudinal axis, and then make a longitudinal cut, then try twisting it again. If it wasn't for the requirement of a tube-shaped profile, then steel would be the perfect choice. However, there's currently no technique that I know of that can manufacture thin-walled square steel tubes that are flat and straight enough. Now, titanium and steel are both tricky materials to process, but titanium has the advantage of having a 40% lower density, meaning the walls can be 40% thicker while still weighing the same. At this point, I'm giving you a very brief mechanical engineering lecture. If you bend a beam or a shaft, there is an axis along which there are no longitudinal stresses or strains. It is called the neutral axis. The further away material is from the neutral axis, the more it does contribute to the beam's resistance against bending. In oversimplified terms, large structures with thin walls are better than small structures with thick walls. So a 20 by 20 tube with 1 mm wall thickness will be more rigid than a 10 by 10 tube with 2 mm wall thickness, while weighing the same. In mechanical engineering, the second moment of area is used to characterize this behavior. Let's determine the second moment of area for a couple of different variants for our gantry. For the examples, we are going to focus on bending and not torsion. Let's start with a 20 by 20 extrusion that is commonly used in DIY printers. Calculating its second moment of area by hand is no easy task, but you will find this information in the manufacturer's datasheet. The 0.72 are a typical value. Let's move on to a 20 by 20 square tube with 1 mm wall thickness. Here we can actually calculate the values by hand, but I'm not going to go into detail in this video. Its second moment of area is 0.46, so less than the 20 by 20 extrusion. Last but not least, I've added a typical linear shaft with 12 mm outer diameter and a 6 mm bore for comparison, which has a second moment of area of 0.1. I would like to point out that at this point the material is not in the equation yet. We are simply comparing different geometries. To complete the picture, we need to look at the materials from which the different profiles are made out of, or to be more specific, the Young's moduli and the densities. The extrusions are exclusively made out of aluminium, whereas with the square tube we will look at both aluminium and titanium. The linear shafts are made from steel. To get the bending stiffness of the structures, we now multiply the Young's modulus with the second moment of area. I'm not going to go into units here and just compare the numbers. The smaller the number, the more the beam will bend and deflect when the same force is applied. Let's look at the different results. The 20 by 20 extrusion made from aluminium is on the same level as the 20 by 20 titanium tube, followed by the 20 by 20 tube made from aluminium, and the least stiff is the 12 by 6 shaft made from steel. So if you were to apply the same force to all structures, the aluminium extrusion will bend the least, whereas the steel shaft will bend the most. The last key figure we must look at is the mass. The aluminium profile weighs 480 grams per meters, whereas the aluminium tube weighs less than half of that, 216 grams per meters. The titanium tube is right in the middle, weighing in at 360 grams per meters. And last but not least, we have the steel shaft, which is the heaviest by quite some margin, weighing in at 666 grams per meter. To get the big picture, we now have to put the bending stiffness in relation to the weight. Again, I'm not going to put great focus on the units. The clear winner is the aluminium tube, 148, meaning it is the most efficient in terms of making use of its mass. You can see that it has less than half of the mass of the aluminium extrusion, but more than half of its bending stiffness. It is followed by the titanium tube, 133, which is less efficient simply because the Young's modulus to density ratio of aluminium is slightly better than that of titanium. And the 12 by 6 steel shaft has by far the worst efficiency out of all four. This has nothing to do with it being out of steel, but simply because you have a small structure with thick walls. So what can we conclude from all of this? Generally speaking, tubes are a better choice than extrusions. Regarding the material of the support structure, aluminum is the best choice for non-enclosed printers, as it has a high Young's modulus to density ratio and is easy to manufacture. For enclosed printers, steel would be the best choice. Unfortunately, it's difficult to manufacture thin-walled tubes from steel. So the next best thing is titanium, with a thermal expansion that is very close to steel. Is there a catch to titanium tubes? Well, a small one. While titanium is easier to process than steel, in the context of this video at least, it is still not possible to achieve perfectly flat tubes. But due to Klipper's powerful bed mesh algorithm, this is not really a problem, since the bed mesh does not drift over time anymore. Thank you very much for watching and see you next time. Bye.